So the question is topological sort. Actually, this question I have solved in a previous video of mine, but I have solved in that video using the DFS algorithm. Now in this video, I am going to solve this question using the BFS technique that is known as the breadth first search, and which is also known as for topological sort Kahn's algorithm. So in this video, I'm going to discuss the details of the Kahn's algorithm for finding the topological sort of a directed acyclic graph. Okay, now it's so we know that the graph can have a multiple topological sorts. So its one order can be of 5, 4, and 2, 3, 1, and 0. Okay, so as we can see that 5 to 0 there's an edge, so 5 is coming before 0. 4 to 0 there is an edge, so 4 is coming before 0. 2 to 3, and so on. Basically this satisfies the topological order of the DAG. So the algorithm now, okay, now the algo first declare a first for simple BFS we require always require a queue. So I have declared a queue here, queue data structure that follows the first in first out condition, and in this case we require a extra array which we will call in this case as in degree array. So why call in degree? Basically, we will be requiring the in degree of every vertex. So what is in degree? In degree is nothing but basically the number of incoming nodes to a vertex of a graph. So for 0, I can say the number of incoming edges are 2 basically. So for 0 it is 2. For 1 it is also 2, and for 2 we can say there is only a one incoming edge, so it will be 1. For 3 it is 1. For 4 it is 0 because there is no incoming edge, no incoming edge for 4 and 5, so it will remain 0. Now what the algorithm says that first initially the vertex which have in degree 0 vertex with in degree 0 are pushed to the queue. We have to push them to the queue. So we will push 4 and 5 to the queue. And now take the front element, take the front value from the queue. So we will first take out 4 and include it in our topological sort. So what I will do now, we have to take the adjacent node of 4, that is 0 and 1 in this case, from the adjacency list, and we have to basically decrease the degree of adjacent nodes by 1. So what I will do, its adjacent nodes are 0 and 1, so it will become 1, it will become 1. Okay, so the one call is over. So now we take out 5 from the queue data structure and see its adjacent node, which are 0 and 2 basically. So I will reduce its in degree by 1, which will become 0, and 2 it will become 0. Now the third step is at fourth, basically fourth. So if at any point in the loop the in degree of any vertex becomes 0, we will push that vertex to the queue. In this case, 5 adjacent nodes are 0 and 2, and their in degree are also 0, so we will push 0 and 2 to the queue. Now we will take out q 0 from the queue and insert in our topological sort, and now we see there is no adjacent node to the 0. Now its call is over, and we now take out 2. Now 2 adjacent node is 3 basically. So 3 in degree, we first reduce the in degree of 3 and check whether it has 0 or not. So it is 0, so we include it in our queue. Now we only 3 is there in our queue, so we take out 3 from the queue and check its adjacent node. Its adjacent node is 1. Its in degree is still 1. So first we decrease its in degree by 1, which will become 0, and now we will push 1 to the queue. Okay, so now there is only one element which is 1, so we take out 1 from the queue and see its adjacent node. There is no adjacent node, so basically this is over. Now we see that this is 450231, which is not similar to this, but it is, as I said earlier, that any graph can have a multiple topological sort order. So this is also one type of order. We can see that it follows the topological sort. Basically 4 is coming before 0, 5 is coming before 0, 2 is coming before 3, 3 is coming before 1, 2 is coming before 3. So it basically completely follows the algorithm and topological sort also. So now the time complexity of this, since we are using the BFS for the directed graph, its time complexity will simply be the V plus E, because we are traversing an each and every vertex and edge of the graph. Space complexity will be simply maximum O of V, because of the array we are using and the queue data structure. Okay, so okay, now let's code the solution for this. Okay, so the now what I have to do basically, first I have to declare the n degree, because I am using the sum of the at the extra space, so I have to declare them as well basically. So these are like, first I have to declare the n degree and I have to fill the basically the n degree array, n degree vector. So what I will do, vector of n degree basically of size v and filled with 0. Now actually I have to fill it. Now how to fill the n degree vector? So as we see that we have to increase the number of incoming edge to a vertex. So what I will do when I am going from 0 2 to 3 basically, so I will increase the n degree of 3, because there is an edge from 2 to 3, so 3 will have incoming edge and its count will be increased. Okay, so I will do like this basically, for int I equals to 0, I less than v, I plus plus. I require a second loop as well actually for here. Int j equals to 0 and j less than adjacency of I dot size and j plus plus. I think yes, it's right. Now what I will do, n degree of adjacent of I and j, I have to increase this basically. Okay, now through this loop our n degree array will be filled. So now what I'll do, I will just declare a queue data structure which I am requiring for the BFS calls. So basically queue. Now as I told, I have to insert the vertex with n degree 0 initially. So what I will do, I will just loop the n degree array up to v and I plus plus. If at any point in degree of I equals 0, then I have to just simply q dot push the I. Okay, now this is complete. Now I simply just have to the traverse the until the my list yeah, the not list but queue becomes empty. So while queue is not empty. So apart from this, I have to declare the answer array as well, because I have to return the vector and answer. And int I first take out the front element of the node. Okay, yes, from the queue, and I should pop it to keep the loop going. Now I should push this node into our answer array basically at this moment only. Push back node here. Now I have to traverse its adjacent node. So that is auto I adjacent of node, basically. Yes, okay. So when I visit any adjacent node, I have to first decrease its n degree of I minus minus by 1 and check whether its n degree of I equal 0. If it is 0, then I should push it to the queue I. Okay. Now the code is, I think the code is complete, and eventually when the queue becomes empty, the topological order will be stored in the answer array, and after this I can simply return my answer. Okay, now let's check the code. Some compilation error, I guess, at the 84th line. Where? Oh, actually, I found the error. I was actually missing curly braces over here. So I just put it, and I think the curly braces are now fine. And I should run the code. I think it should give the right answer. Yes, actually, it is giving the right answer. And it is running for all the test cases. And that's it. The code is this, and the explanation, I think I was able to explain the code. Thank you.